very like uses maps and list comprehensions. And oh, Yanni's here. Is he checking up on me? Probably. What time is? Oh, 2 after. Oh, my clock is slow. Okay, sorry, I should be lecturing. Sorry, guys. Just have to make sure that all of the things are correct. Presentation mode. This. Okay. Right, so let's get things started. First, I need to know if everyone can hear me. Oops. Can you hear me out there in chat land? Yes, can you see? Can you see what's on the screen? Yes. I just gotta put this in for the echo. Enough. Okay. Just for Yanni, there's a few hundred students here today. Packed room, standing room only. Don't verify me. Okay, so what have we been doing? We'll just make sure that this is all running. So last week we started talking about polynomials and how they form a ring. And what I want to get to today is show you that the polynomial ring actually forms a Euclidean domain. That is to say, we have GCDs on polynomials, right? So there's just a few more operations that we have to define. So I ended up correcting, where are we? We are here. All right, so let's just start here again. So very quickly, we're working in the polynomial ring Rx. The script R denotes any ring, and a ring is something with addition, where you have a 0, where you have subtraction. You also have multiplication, which distributes over that addition, which also has a unit, right? So some multiplicative identity. My claim is that the rings form such, that the polynomial ring forms such a ring. So we denote a polynomial by this, right? We have terms, and a polynomial is the sum of terms. Every term is comprised of a coefficient and a monomial, which has a degree, right? So this is the leading term as it happens, which has a leading coefficient a n, leading monomial x to the power of n, and then the polynomial has degree given by the degree of its leading monomial. So this is a polynomial of degree n. Remember, by convention, the leading coefficient of the 0 polynomial and the leading term of the 0 polynomial is 0, and the degree of 0 is minus infinity. This should help you with some edge cases in your programs. All right, so we had this representation for terms. We can spin up the 0 term. We can spin up the 1 term. We talked about the structure of polynomials. You should be a little bit familiar with it now, having worked with that project, which I hope is going well. Okay, so here I've corrected addition. Now there's actually a base case. So if you're trying to add 0 to anything, so a plus 0 is a and b plus 0 is b. That's what this says. So now that should work, even though it was pseudocode in the first place. But the addition routine that we have sort of does something a little bit unwise. This is naive. This is probably the worst addition algorithm that you can write, but it should work. Right, so we're not trying to write the best addition algorithm in this instance. I'm just trying to define addition on polynomials because we need addition on polynomials for them to be a group. All right, so there's my definition of addition. Now, I'm not going to sort of prove this, but it should be clear that if you take something like this and you add something like this to it, you get something that looks like it. Right? If I had a b, which was comprised of the sum of sort of coefficients denoted bm through b naught, simply putting a sum between those things would act as the sum of those polynomials, right? It's just that this is this weird interplay between something true in math and true in computer science, right? So if I have f and I have g, f plus g is already their addition to mathematicians. You don't really have to do anything else. On the computer, we actually want to resolve it so that terms of similar degree will combine their coefficients, but it doesn't really matter. Okay, so it seems clear that if we add two polynomials together, we're going to get a polynomial. Like nothing funny can happen there. Do we have something that acts as the 0? Yeah, the 0 polynomial acts as the 0 in this group. Do we have negative numbers in this group? Does every polynomial have an inverse additive? Yeah, so what's the inverse of x squared minus x? Well, minus x squared plus x. You just throw a negative symbol in front of your f, and that's its additive inverse, right? F minus f is 0. Okay, so we have addition. So it seems that the polynomials at least form an additive group. Okay, so now we need to do multiplication, and then the claim will be they form a ring. All right, so here's my multiplication. And again, this is what we're going to define multiplication on polynomials to be. I'm saying you give me two polynomials, a and b, with integer coefficients and their univariates. And I'm going to output the product of the polynomials. Now, if either of the polynomials are 0, 0 times anything is going to be 0. Okay, so that's where that base case comes from. So there's a stopping condition in this recursion. Otherwise, if the leading terms of the polynomials are the same, then we're just going to return. Sorry. This is a cheeky way of asking if the polynomial is comprised of a single term, like x cubed. X cubed is going to be equal to its leading term, because the leading term of x cubed is x cubed. Okay, so if the polynomial, the a and b that are coming in are of single terms, this is kind of a weird edge case. Right? So I'm saying if they're comprised of exactly one term, then just multiply them together. Well, how did I define multiplication how can I use multiplication when defining multiplication? Well, again, this is the weaker multiplication. And we already discussed, do you remember that terms are actually closed over multiplication, right? Ax to the n times bx to the m is ab times x to the n plus m, right? Those are two terms multiplied to a term. Right, so this actually is a multiplication of polynomials. This is a multiplication of terms. So I've taken the problem of multiplying polynomials and reduced it to something lesser. Okay, so they're not 0, and the polynomials both have at least two terms. Otherwise, they would have triggered one of these if statements. By this point, we're assured that the polynomials are non-zero and have at least two terms. So I'm saying just take your polynomials and break them up however you want into two pieces. Write a is equal to a1 plus a2. Now you can't cheat, right? You can't sort of say, 2x squared is x squared in this part and x squared in the other part, right? The terms of same degree you can't discompact them. Okay, so effectively that's what this constraint ensures. I'm saying take a and write it as a1 plus a2, where a1 and a2 can't have the same degree. That's actually a weaker restriction. You just can't take the leading term of these two things and pull them apart. Okay, so take a, it's written sensibly, and then break it apart in any way that you want, and do the same thing with b. And then all we do is we use the distribution property. We exploit it here. I'm saying, okay, so I want to multiply a times b, which is the same thing as multiplying a1 plus a2 times b1 plus b2, which, if I distribute this, is equal to a1 times b1 plus a1 times b2 plus a2 times b1 plus a2 times b2. But what is true about these individual products relative to what's coming in to multiplication? They are smaller. Each of them are smaller. So I've taken the multiplication problem and reduced it to a bunch of smaller multiplication problems, where eventually we're either going to hit the case where one of the terms is 0, or the polynomials have one term only. Okay, so this is a definition of product. I think the simplest one, right? And actually, it's a divide and conquer algorithm. It's going to be a little bit better than the naive algorithm that we put into your project. But we could take this and we could confirm then that if we take f times g, that something is produced within the ring. That seems pretty clear that that's going to happen. Okay, so it's closed under multiplication. Do we believe that we have a multiplicative identity here? Is there something that I can multiply f by to get f? That's a polynomial. 1. Okay, so we do have multiplicative identity. We just sort of have to show that the distribution property works here, and then we'd get our ring. But these are simple proofs. They're just sort of detailed. You just write an arbitrary f and an arbitrary g, and you just multiply them together and show that it remains in the ring. Okay, so here's our multiplication. This is how we're going to multiply terms together. So this is just an edge case to make sure they're not 0. But otherwise, just to take the terms. a term times a polynomial is this, and a polynomial times a term is this. This is just a cheeky way of not having to define this twice. Right? We just define this by reversing the input. What are we doing to here? We're going to map. Oh, so this is, yeah, this is how you take a term and you multiply that term by a polynomial. This is like left distribution, right? And they're saying, oh, just take that term t and multiply it against every term of the polynomial. So that's what this map is doing, right? Map multiplied by t every term in here, okay? And then this is how we're going to end up multiplying, which is why you're not going to get that significant speed up in your project, because this is like the world's worst multiplication algorithm, right? I'm going to say, okay, so to multiply P1 by P2, I'm going to look at every term of P1 and then distribute that over P2 and just collect the adds. It's going to work. It's simple. It's correct. But it's the slowest one that I possibly could have written. Like, for one, I had a divide and conquer version of this up top. Like, if we were to be more clever, like this is this. It's just that the way I've chosen to split up these polynomials is always into the leading term and the rest, right? Which is going to be the worst case for the divide and conquer. So doing something like this would be better. Really, what we want to do is interpolation. Remember last week I said, in order to get f times g, you just need a few evaluation points and to interpolate through them. That's way faster than doing this. So what you have in your system currently works, but is slow, right? So if you're not getting these incredible speed ups, or if you think your computer is turning away, yeah, because this is a basic computer algebra system that we have written, and the idea is that you can take these pieces out and improve them, and everything else will improve. So we should be happy with correctness. Like, this is how software really is done, right? You don't get to the optimized version first. You get some working prototype that undertakes improvement until it's releasable. So just to show you that this indeed works. Oh, I shouldn't have done that, actually. So let's see. X is a polynomial. So you always have to make sure to do this. This is the tricky thing that we're doing to enforce an interface to the user who wants to use this so they can't create weird polynomials, right? They always, and it's nicer. I want to be able to enter things in like this. So there's P1, there's P2, and there's their product. Oh, look. This already implemented the pretty printer. Because I coded it the other day. So look how nice it looks with the Unicode printing and all of this stuff. Cool. I hope you guys have checked all of the edge cases. There can be some pretty weird edge cases, especially with the flag to reverse the terms. Just be careful. Be careful you're checking zeros. Okay, so the following properties are consequences of our definition. I'm not going to prove them, but you could simply prove them. If R is an integral domain, and remember, this means that we're in a ring where no zero divisors are present. Right, so there's no two polynomials that multiply against one another to produce the zero polynomial. Okay. If we have A and B, here's a few properties that should be obvious. The degree of the product of two polynomials is the sum of their degrees. If you disagree, tell me. Okay. The leading coefficient of A times B is the product of the leading coefficients. That's a predictable term. The leading monomial of the product is the product of the leading monomials. And the leading term of the product is the product of the leading terms. This is pretty easy to demonstrate. Like, here is A. That's like arbitrary polynomial. Here's B. It's an arbitrary polynomial. There are two terms that we can immediately read off of the product. Which two terms? The leading term and the tail term, I guess. Right? The very last thing, the thing at the bottom. Right? Because this will multiply by this, and that's going to be the only term of degree n plus n. And then we're going to multiply A naught by B naught, and that will be the only term of degree 0, or the smallest degree, right? This still holds even if that isn't the constant one, okay? So every field is also an integral domain. This is going to be an important fact later. I'm not going to prove it, but it's provable. This should have been something you proved in your Algebra 2 or something like that, so just keep this in mind. Okay, something for your project. Okay, so we're going to take this sort of naive, terrible multiplication algorithm and make it a little bit better, okay? Because you need to work with big ints. And to utilize a big int, that is an integer that the computer is going to presume can be as large as we want it to be, that is going to be slower than using machine integers, because machine integers can be multiplied and added very quickly, right? That's what literally the algorithmic logic unit on your computer is responsible for doing. Your computer is like purpose built for doing multiplications and additions, right? So we should use them. Okay, so we talked about this game that we could play, or if I had a number in mind, you could ask me what that image of that number is, any mod p, and eventually you can recover that number. And I actually gave you an algorithm for recovering that number. So all I want to do is deploy this on polynomial multiplication. Let's jump to just the example, because I think if we look at the example, sort of it becomes clear what we're going to do. So instead of doing the products across big int, which is expensive, we're going to do products in a field instead. Right? So instead of doing the product zx, we're going to do the product, in this case, z5, z7, z3. Okay? And when we do the product z5, this is the product, right? 3x squared plus x plus 0. When we do the product mod 7, we get 4x squared plus 5x plus 1. When we do it mod 3, we get 0x squared plus 0x plus 1. Furthermore, since A was degree 1 and B was degree 2, we know their product has to be degree 2, has to be quadratic. Okay, so what am I saying here? The leading coefficient of the product is 3 mod 5, 4 mod 7, 0 mod 3. What does that sound like? Oh, that's the answer. But that sounds like something the Chinese remainder theorem is primed to solve. Right? So you just do that for every coefficient down the degrees, right? So we'll do the next one. I know that the product, the linear term of the product, mod 5 is 1. I know mod 7, the linear term is 5. I know mod 3, the linear term is 0. So then you use Chinese remainder theorem, and then you recover the linear term. And then you do the same thing for the constant term, right? So here, what's down here? 340. Yeah, so 340, you get 18. 150, you get 96. And 011, you get 85. Right? That's the solution to that. So my claim then is, okay, so the product over the integers is 18x squared plus 96x plus 85. But clearly that's wrong since there's some negatives in here. But this is why we're going to use the symmetric mod. The symmetric mod is going to help us recover the negatives back, right? We just have to sort of shift this a bit. Right? So if we use the symmetric mod instead of the mod, then instead of getting 18, 96, and 85, we're going to get out 18 minus 9 and minus 20. Right? These are the same numbers. We're just having a different canonical representation for that equivalence class. So then in the end, we get 3x minus 4 times 6x plus 5 is 18x squared minus 9x minus 20. And then here is pseudocode for doing it. I'll have to go back and talk about the theorem. But really all we want you to do is implement this multiplication algorithm, okay, which just utilizes Chinese remainder theorem. Now, there's one difficulty here. Here, I did it in such a way where it seems that you're going to do all of it at the same time. Like I'm giving 3 polynomials here. We don't want to do that. Like I don't want to spin up a bunch of copies of the multiplication problem to give to Chinese remainder. What I want to do is update, right? So I know what the solution is mod p, right? And then I can update that to know the solution mod pq. And then I can update that to know the solution mod pqr. Because in Chinese remainder theorem, you don't actually need all of the things you're modding out by to be prime. You just need them to be co-prime, right? So it's okay. Like I can solve the Chinese remainder theorem mod 8. That's fine. That's also not 8, 6, because that's 2 and 3. And then I can like add 5 to it and have a solution mod 30. Okay. So here, right, we're going to, this is what the loop is for, right? You're going to update the product with the new prime, right? Which just gets you a little bit more like wider coefficient range until it's finally so wide that you've actually captured the answer. Now the question becomes, well, when do I stop? Right? Like when, because I'm saying that the product of the things that you're modding out by has to exceed b. So what's this b? Okay, so we'll go back to the statement here. Okay, so multiplication by Chinese remainder, which is explicitly part of your project. So let's define a. It's just an arbitrary polynomial. We always write it like this, right? It has coefficients an through a naught. It has terms monomials xn through x to the 0. I'm going to define something called the height. Have you ever worked with these norms? one norm, two norm. This is sometimes called the inf norm, right? So we're going to define the height or the inf norm of a polynomial to be the maximum across all of the absolute values of the coefficients. Okay, so just look at all the coefficients, take their absolute value, pick the largest one. That's the height of the polynomial. So for instance, 2x squared minus 5 is 5, right? Because it's two coefficients. If you absolute value them are 2 and 5, 5 is larger than 2. Okay. Further let hashtag A or pound A. I don't know what you guys call this now. You're all. You call it hashtag? And we're about the same age, right? So it wasn't always hashtag.
No. It
was bash. Yeah. This was a number. This was on the telephone dial. I don't know what the hell it does, but it was there. Before this was a hashtag, it had other uses. Okay. So hashtag A's, we're going to let that be the number of non-zero terms of A. So for instance, the number of non-zero terms of 2x squared minus 5 is 2. Okay, so now we have the height of a polynomial. I know the number of non-zero terms of a polynomial. So if we intend to use the Chinese remainder theorem to calculate the product, C of A times B, where A and B are now taken from this sort of prime field. If we want the product over the integer coefficient ring, then we need an M, that's a product of primes, that is larger than 2 times the height of C. Okay? What's the problem here? Well, what am I saying C is? The product. So how am I supposed to read the height of the product in order to get the product? Okay, so clearly we have to do, so we study analysis in here, right? You guys have done a lot of math with less than and greater than symbols. So this is a bound. So we just make a less sharp bound, right? That's like higher than this one. Okay, so we do not have access to C. I should mention here, this even is insufficient because if we want negative numbers, I actually need twice as many of these, right? If I'm saying the coefficients can go from like 7 to minus 7, right? So this is saying the height of the polynomial of the product is going to be like this. Remember, the height is telling us how large the coefficients are ever going to get, right? So I'm saying, okay, the height of C is this, but I don't, like that may have been absolute valued, right? That the height could have been a plus height or a minus height. So I actually need all the numbers 0 to that height and 0 to minus that height. So the size of that set is 2 times the height of C, which we can't even get. Okay, so here's another statement. I'm saying the height of C is bounded by the height of A times the height of B times the minimum number of non-zero terms among A and B. And you can prove this. It's not hard. It's just really detail oriented. So the way that you can do it is say, okay, here's A. Just replace A's coefficients by alpha and like call alpha the height of A. So like literally like every single coefficient in it is its largest coefficient. The same happens to B. Multiply them together and do a worst case analysis on like how big the coefficients are going to be. Like use binomial expansion or something. Like you should be able to figure this out. We won't do it. But in the end, right, that's the bound that you need. And if you go down to my, okay, so here was our example, or I wanted to multiply A times B. You see the largest coefficient in here is going to be 20, right? So we better get a number system that's at least has positive 20 and minus 20. It has to be at least 41 numbers if you include 0. So the height of A is 4. The height of B is 6. The number of non-zero terms of both of them is 2 each. So 4 times 6 times 2 is 48. And 48 is wide enough for us to be able to capture that minus 20 back. Do we need this min? No. We could have made it max. That just makes it a less sharp bound, right? Wouldn't just the heights work? I'm gonna say no, because like because this is the statement. No, I'm not sure it's that simple because yeah, adding together. Yeah. If I'm wrong, put it on the ed stem, but I'm pretty sure I'm pretty sure it can't be this simple. because again, like terms can collect, and then like your coefficients can get much larger. Yeah, just give it a try. Multiply that out for like small examples, and I'm sure you'll see, even if you do it for like 2 cubics or something like that. Okay, so you have the Chinese remainder theorem. I've given you a bound to work towards to know when you can stop doing Chinese remainder, because you're assured to have this to have the solution over the integers. There's actually something called rational reconstruction. Believe it or not, had we started this problem with fractions, we could do Chinese remainder theorem and actually recover the fractions that we started with. That's a little bit more complicated. It's a breathtaking piece of technology. I can't believe that it works. My last supervisor is the one who invented it. I don't know. You know who Borwein is, or Plouffe? You never heard of like the BBF algorithms? You know when they like have a supercomputer and they like say, "Oh, we calculated like the 10 trillionth digit of pi." This is all Borwein's algorithms, effectively. He was like the king of pi, right? He was a really neat dude. Okay, so we have this. You have a bound. So now you should be able to go home and implement this multiplication algorithm, which is doing one step of CRT. Like when we're going to update, and I'm saying, look, you have this product of primes, right, that you're collecting in the Chinese remainder theorem, and you can stop doing this when that product exceeds B, which is this bound. And I'm being a little bit cheeky here. I'm not actually counting the number of non-zero terms of A and B. I'm just setting it to n, because clearly it's less than that, and clearly it's less than there. Although, you know, if you did a little bit more of a sharp bound, you could get some computational advantage from that. I'm just being a little bit lazy. Okay, so you want to implement this. This is the update algorithm for Chinese remainder theorem. So you give me, this is a little bit more generic, because I'm saying you give me 2 polynomials, one in Zn and one in Zm, right? These aren't necessarily fields anymore. I just want the GCDs of these 2 things to be equal to 1. Right, and then this will give you one combined step, and then this table here is a problem. What's the initial problem? Oh, it's just this initial problem. I just gave you more evaluation steps. Right, you can use this for tracing your code, right? If it's not working, you usually want some type of worked example when you're programming, especially in this discipline, so you can ensure that your code is actually producing the thing that mathematically we're expecting it to produce. Is there any questions regarding that, since it is sort of explicitly one of your homework tasks? I'm only asking because I wanted some chocolate, but
and then you get your information that you apply to get.
Because you'll do it once and you'll get like an answer mod PQ. And then I'm saying, oh, I have another one mod R. Can we add that to it? And the answer is, yeah, no problem. Right? Because as long as R was co-prime with PQ, you're fine. Right? Now there's like, we can solve it as vectors. And then you may be, and that's sort of programmatically easier, but it's a disaster, because if you have to make a vector, then you have to copy the product, all right, so many times, and these things may be huge. And remember, we're trying to make this more efficient. That's the object of this. If I was really in charge, you'd have to do this and interpolation. That was the original thing I wanted you guys to do on the project. You would have got pretty good. You would have got huge speed up going from the most naive multiplication algorithm to interpolation with Chinese remaindering theorem. But that was vetoed. Originally, they wanted me to teach you how to do integration automatically, but it's not that interesting. You just do a really big partial fraction expansion, right? Everything looks like a ln, and then you integrate because you know how to integrate logs, and then you use simplify to bring it all back together. And anything you can't integrate, you just look up in a table. This is much more fun than that, believe me. Okay. So we have addition and we have multiplication. So the polynomials are in fact a ring. Now, they're not going to be a field. That's off the table, right? Because we can't divide x by x squared, right? We can't divide the coefficient 2 by the coefficient 4. Okay, so the best that we're going to be able to do is sort of get this like partial fieldness, right? To get the remainder in quotient algorithm. That's sort of like halfway to division. And if we have the quotient and remainder algorithm, that gives us the GCD algorithm. And that means the polynomial ring will be a Euclidean domain, which we need. The GCDs are so important for the factoring algorithm. Okay, so I'm just going to remind you about division. So remember we did division. You should have done a little bit in high school. You definitely should have done some in calculus, doing these integration by parts, but that I just mentioned. Every year we seem to lose a little bit of theory. So would you know how to integrate f over g if f and g were polynomials? Okay, so step one, right? They say if the degree of f is larger than the degree of g, you must do a synthetic division. Okay, so we just need to program that somehow. So I have a couple of like hand examples to work through this, because it's just literally identical to what you've been taught, except there's a little bit of a different perspective that we have to take when working in Z11 that you may not be used to. Okay, so I want to divide 10x squared plus 4x plus 1 by 5x minus 3. And my claim is that this is going to, well, the other week I actually said all you have to do is evaluate this at x equals 3/5, right? Or 3 times inverse of 5 mod 11, right? So you can check me on this. If you take, what is this? What's the inverse of 5 mod 11? Well, you're going to get 7, right? If you evaluate this at 3/5, you're going to get 7 if you take it mod 11. That would have saved you a hell of a lot of time in calculus. That's why we didn't tell you. Okay, so let's just undertake the long division algorithm. So what is the, I believe this is the numerator. This is the denominator. So we're dividing out by this. So the object here is to try and multiply this polynomial in such a way that we're going to eliminate the leading term of this, correct? Okay, so 10x squared is in here, 5x squared is there. So if I multiply this by 2x, you get 2x times 5x is 10x squared. 2x and 8x make 16x, but mod 11, that's 5. If I say something that's confusing, you got to stop me. I don't want to repeat all of this. Okay, so everyone's still with me? Okay, so 10x squared plus 4x plus 1 minus 10x plus 5x. So this disappears, which was the objective. 4 minus 5x is minus 1x, which is 10x mod 11. This comes down. Okay, so now we need to eliminate 10x plus 1. How do we eliminate 10x plus 1 using 5x plus 8? Well, I have to get rid of that 10 again. So I'm going to multiply by 2. We're going to get 10x plus 16. 16 is 5 mod 11. Their difference is 0 here, minus 4, which is 7 mod 11. So that's 7. Since this is less degree than this, I have to stop. There's nothing I can multiply this by where this is going to disappear. So this is the stopping condition of the remainder algorithm. And then we recover this 7. Right? So we can get the quotient here and we get the remainder here. So thus, 10x squared plus 4x plus 1 is the quotient times the numerator plus the remainder. Okay, is this okay? Because we're going to go to a more complicated one now, right? Is it okay? Okay. Where? This? Cut it off. It's here. That's the 16.
Let's say,
2x times 8. 2x times 8 is 16x, which is 5x mod 11. Oh, yeah, that part isn't there yet. Like, sorry, I can't. Yeah, it's hard when I'm not writing on the board. But good point. Okay, so that's the easier one. So let's just study, how did we actually produce this 2x? Like I'm saying, oh, we had to multiply this by something to get 10x. But like, what is this systematic way of doing that? Or let's just say division, right? Like, so I know this is, okay, so the question is, what do I multiply this by to get that? So it's this divided by that. So what's 10x squared divided by 5x? Well, that's 2x. Okay. And we're gonna do that in a different setting. So that one I designed in such a way that all the divisions were clean. Okay. This one I did it in such a way where the divisions aren't clean, but it shouldn't matter to us because the computer is handling this. Okay. So we just have to implement it properly. Okay. So I want to divide 5x cubed plus x squared plus 2x plus 6. by 3x squared plus 1. So let's undertake this. Okay, so I need to get rid of 5x cubed, and I get to multiply by 3x cubed. So the question becomes, what do I multiply 3x squared by to get rid so that its difference with 5x cubed is 0? And we said it's this divided by this. Okay, so that's 5x cubed divided by 3x squared, which we can write if we want as 5/3 x mod 7, right? Like I know we normally don't write fractions, but if we just look at this as 5 times inverse 3, right, which is a sensible thing to do in this setting, then the inverse of 3 times 5 is 4. I don't know what the inverse of 3 mod 7 is. We want to try 3, 6, 9 is 2. Wait, am I adding? Okay, I need to figure out what the inverse of, what do I multiply 3 by to get 1 mod 7? 3, 6, 9 is 2, 5, 8 is 1. Is that true? 3 times 5 is 15. Mod 7 is 1. Okay, so that means the inverse of 3 is 5. So 5 times 5 is 25. Mod 7 is 4. Okay, so that's how we get 4x here. Okay, but who cares about all this arithmetic? Computer's going to handle it. Okay, so 4x then times this gives what? This is going to give us 12x cubed, which is 5x cubed, right? Because we're working mod 7. Then we're going to get 0x squared. I like writing in the 0 terms because it makes the sums line up. And then we get 4x. Right? We start taking differences. 0, perfect. That's exactly how we set this up. This is called doing that cancellation is called a syzygy. Right? There's a special name for this. X squared minus 0x squared is 1x squared. That's fine. 2x minus 4x is minus 2x. Mod 7 is 5x. Okay, and then we also bring down that 6. Now we have to get rid of this x squared. So the question becomes, what do I multiply 3x squared by so that its difference with x squared is 0? Well, it's this divided by this. So it's x squared divided by 3x squared. X squares cancel. We're left with a third mod 7. We just learned that the inverse of 3 mod 7 is 5. That's why 5 goes there. Okay, so 5 times this is 15x squared, which is 1x squared mod 7. Then we get 0x, then we get 5, and their difference gives 5x plus 1. Right? Yeah, all of that works out fine. So that's the remainder, right? Because this is lower degree than this. So there's nothing that we can do to eliminate that. Right? Because we can't multiply by 1 over x. The least that we can multiply is by a constant. There's no constant that we're going to multiply this by in order to eliminate that. Right? So this is the remaindering algorithm with just a little caveat that these inversions are happening in sort of this residue class. You just got to remember where your arithmetic is happening. That's the sort of wrench I'm throwing into this. It's like, these are all basic algorithms. I'm just saying, oh, you just don't use all the numbers. Use a different number system. Okay, so that's there. I believe I also here this is I'm going to show you the division algorithm, and this is the exact same example that we just worked through, so that you can use this to trace. I don't even think you don't have to do anything with the division algorithm, if I remember right. There's nothing in your project about going into it. I don't think so.
We just had to set the prime, but that was to print.
Oh yes, yeah. Okay, so that's a good point actually. So what was necessary for us when doing this division algorithm? Like we had to be we were working in a one of these fields. Like the coefficient ring had to be a field. We were saying like I need inverses. All right, so because I need inverses, like how am I supposed, like how do I account for that? Like when I'm actually writing the computer program to do it. All right, so this is why division has this funny interface. Division says, look, I'm happy to divide or do quotient and remaindering for you. But you have to tell me what field the coefficients are presumed to be coming from, because I need to do inversion. Okay? There's a different way that you can do this. There's something called pseudo division, where every time that you are dividing, you get to multiply by anything you want as well. right? So you get remainder quotient in some constant that everything has been multiplied through by. And this is a way to actually to do division in such a way where you don't need a field of the coefficients, but you do produce some stupidly large auxiliary factor. But it's just interesting. You should know that the pseudo versions of these algorithms exist, right? That just let you multiply out by whatever is in the denominator at any given time. Okay, so if we're looking at polynomials now and their coefficient ring is made to be a field, then the resulting ring, I guess, is a Euclidean domain, right? So this is a ring, right? Polynomials with coefficients taken from a field is a ring. The coefficient ring is a field. So just make sure we're like distinguishing those two things properly. Okay, we'll never get inverses here. So this is a Euclidean domain, which is important, which means we get division, we get quotient remainder, and importantly, the GCD algorithm. Here's the theorem of division, right? I'm just saying if you give me A and B, two polynomials from f of x, and b is not equal to 0 because we can't divide through by it, then there are unique polynomials q and r, quotient and remainder, from the same ring, such that a is equal to bq plus r, and r is 0, or the degree of r is less than the degree of b. It's not actually too hard to do uniqueness. I've been skipping all of the proofs, but why don't we do one of them just for funsies, right? Suppose that this wasn't a unique operation, that there was like two ways that I could divide a by b. There are two ways that I could divide a by b, then there should be two distinct quotients and two distinct remainders, right? In particular, the degree of R1 and R2 should be less than the degree of b, right? That's this requirement. Okay, so suppose that we do have these two quotients and two remainders. Then these two things are equal to one another, right? BQ plus R should equal A, right? This is equal to A, this is equal to A. Okay, but if these two things are equal, then I can make this rearrangement, okay? But since the degree of R and 1, okay, so I'm saying that the right-hand side here is equal to B times Q1 minus Q2. That is to say, this has factors, right? Like, surely B divides the left-hand side, right? Because B is there. So if B divides the left-hand side, surely B divides the right-hand side. Okay, but how can B divide the right-hand side if the degree of B is bigger than both the degree of R2 and R1? You can't divide something that's smaller than you. Okay, well, you can under one condition. Anything divides 0. Okay, so if this really is the case that B is dividing this difference, then this difference is 0. And if this difference is 0, then the remainders are the same. Okay, nuts. Okay, but maybe the quotients are still different with the remainders being the same. Okay, I now know that B times Q1 times minus Q2 is 0. So this could be true if these two things, if B could not be 0 and this could not be 0 and equal to 0. Under what circumstances could that be okay? Yeah, if our ring had 0 divisors in it. But I said we don't have 0 divisors. We proved that earlier on. Okay, so since we don't have 0 divisors, the only way for this to be equal to 0 is for properly one of these factors to be 0. Can B be 0? No, that's like part of the precondition of the question. Okay, so this has to be 0. That's the only option. Okay, but if Q1 minus Q2 is 0, that means Q's are equal. R's are equal. Contradiction. Okay, so if you do find Q and R satisfying those conditions, they are going to be unique. How do I prove existence? I tell you how to construct it, right? I just give you an algorithm for doing so. Okay, so here's the division algorithm in pseudocode. Where this is really the only thing we care about, right? I'm pulling out leading terms of the divisor, and I'm trying to eliminate. I always screw these things. What's the thing inside the division sign? Yeah, let's call it I like that. We have the divisor and the divisee, right? So like, just remember always trying to get rid of the leading term of the divisee one by multiplying the divisor by some special factor so that this cancellation is guaranteed, called the syzygy. And that's what this line does in there. And this is how it's been implemented for you, with this sort of caveat that it can't actually do anything until you give it Q. Right? So if you ask for F and G to be divided, it's going to say, I am prepared to do that. You just have to give me P first. Right? And this is wiser to be able to get why did I want to do this? Well, I don't want to have to copy F every time I want to find this. I want to do a division. Because in the Chinese remainder theorem, we're going to have to do we're going to have to look at the polynomial mod 2, mod 3, mod 7, and so on. So it's okay that this function is just going to be able to do that, right, without sort of copying anything. This is like a wrapper over it, right? So it's sort of spatially more clever. Well, then we ended up killing this because we implemented mod in a really dumb way. But who cares? Again, working computer algebra system, basic working computer algebra system. We can always go and fix things as we move forward. Okay, so there's your division algorithm. We've overloaded base so that like if you use this div symbol, this Unicode symbol, it's going to work. And then we have our remainder. I don't know why we didn't use the double slash here. Does that give you remainder? No, it's fractions. Yeah, what's the remainder? Is there a remainder symbol then? Oh yeah, percent. Yeah. So I don't know if defining. Well, let's check. Okay. So I can do this division, and you see we're going to get back a sort of a function. Now I can do the same division, but say you're working 101. We can also do this just to pull out the third. Oh, so divide is going to give you the quotient and remainder. Div is just sort of an helper function, which just pulls out that first part. I imagine this does the latter. But now I'm really curious if we could do R is equal to, how do we say this? I would have to do P1 mod P2 101. Would this, I wonder if this works. That work? Yeah, well, I don't know if defining RAM actually automatically overloads percentage. Like it may be something in base saying like these two things are synonyms effectively. Well, it seems to be working, the percent, which is neat. Go Julia. Okay. So there's a worked example for you. If you, I don't know, this is for past versions of this course where people actually had to program the division algorithm. But if you ever find yourself bored, like, wanting to program it, here you go. Here's a worked example for you. Okay, so we have all of the technology or the fact that f of x is going to be a Euclidean domain means we get the GCD algorithm. Now, we don't need to do anything to the GCD algorithm because if we look up at the one that we defined on integers, let me see. It's Euclid's algorithm. Like, what are we doing in here? Like, what in here assumes that they're integers? This is just assuming that we're working with some objects which have addition, subtraction, division, and multiplication. That's it, right? If you have those things and they satisfy a bunch of other preconditions, then you're a Euclidean domain. Effectively, because that's the Euclidean algorithm, and it just says, I just need these operations. Okay, so we have done that for polynomials. There's like some nuances here, but effectively it's the same algorithm, right? There's the algorithm implemented, but the pseudocode would be the same over all Euclidean domains, right? You just have to be mindful about like what the arithmetic means in that setting. I don't think this is actually part of your, these may be old notes for students of past. But notice this one like requires that you give it a prime. Like we could have done it the other way. I don't know why we didn't. It's just how the interface ended up working. Okay, so here's an example. So this is x squared plus 3x plus minus 5, and we have minus 3x squared minus 4x plus 6. I don't actually know. Oh, I'm asking what is the GCD of P1 times P2 and P2 mod 101? And we should get back P2 mod 101. Is this P2 mod 101? we get 101 minus 3 is 98. 101 minus 4 is 97. 6 mod 101 is 6. Okay, so this gave us the GCD mod 101. Okay, so we're doing pretty good. You want a break today? Or you just want me to keep forging forward and maybe I'll let you out earlier? I'll keep going because it's easier for me to keep going than it is to give you guys a break. But we may actually get through all of this stuff. So yeah, if we have time at the end, or maybe even tomorrow. So you guys got to study this a little bit, please. And then tomorrow, maybe like this, if I don't have material left, we'll just like hash out the rest of the details that are still kind of confusing, or I can even help you with the project, let's say. But maybe I'm too ambitious. Like maybe I'm not going to get through all of this. I just feel pretty optimistic. Okay. So any questions about what has happened? Because now we're going to move on to like the main point, which is like factorization. Okay, so let's just recall what we've learned, right? We were forming number systems. And in particular, the first number systems we were looking at were those sets of like prime characteristic. That is, we took like a collection of the numbers 0 through n minus 1, where n was a prime. And doing so, we realized that, oh, hey, we can actually have addition, subtraction, multiplication, and inversion on that set, right? So that actually became a field. And then from this, because we had division and multiplication, well, by division, we really mean quotient and remainder. But because we have that and addition and multiplication, we could form the GCD algorithm, which also let us form the extended GCD algorithm, which is the thing that helps us do inverses, right, in a field. Right? Because I'm saying in a field, everything has an inverse, but it's not obvious how to actually obtain that inverse unless you do test divisions across the entire ring, which is a bad idea. Okay, so we have GCDs, we have the capacity to take inverses. Then we took all of that stuff and we ported it over to a weird number system that is the number system of all algebraic numbers as represented by their polynomials, or at least that's the perspective I like to have on them. A simpler way of saying, like, look, the polynomial ring actually has all of these properties too. We can define quotients, we can define remainders, we can get a GCD, we can get an extended GCD algorithm. So why do we want all of these things? Well, I said the main thing that I wanted to show you how to do was take a general polynomial and factor it, right? Because beyond quintics, I always forget, is quintics included, or is that the first one that's impossible to get a closed form? First one that's impossible. Okay, so we only have closed forms up to quartics. And then, yeah, beyond quintics, it's impossible. And then, so what do? Give up? No, okay. So obviously we wanted to be able to still factor things. It's just going to take a little bit more work than plugging into some equation. Right? It would have been nice if every single polynomial had a closed form like that. But alas, we don't. Okay, so we're going to talk about factorization first over Zx, and then we're going to talk about it over Zp. Factorization over Zx is simpler than over Zp. So let's start with a simpler problem. Okay, what do we even mean factoring is? So let's think about the integers, right? What does it mean to factor an integer? Like 12. Break it into a product. That's a good start. But 2 times 6 is 12. Is that a prime factorization of 12? Okay, so for the integers, we had to decompose it into a product of primes with powers. And I believe this is like the fundamental theorem of number theory. Yeah, most subjects come with their fundamental theorem, and that's the one of, yeah, you open page 0 of a number theory book, should say the whole driving technology behind this discipline is the fact that every number has a unique decomposition into prime factors. Okay, what is the analogy from that to polynomials? I obviously want to take a polynomial and break it into a product of smaller polynomials. But the smaller polynomials somehow have to have the property that they're like the smallest possible, okay? So I got to introduce this piece of terminology called irreducible polynomial. So a polynomial is irreducible if any attempt to factor it fails effectively. And how do you fail at factoring? Well, I'm saying I can write A as B times C. But if B and the degree of B is 0, or the degree of C is 0, how can I put this? I don't care about scaling constants on polynomials. I don't care to distinguish x plus 1 from 2x plus 2. Why do you think I don't care to distinguish between those two polynomials? More than that, I only care about polynomial roots, right? I don't care. You can do anything to these polynomials that leave their roots invariant. So what's the root of 2x? What's the root of x plus 1? Minus 1. What's the root of 2x plus 2? Minus 1, right? So if the roots of f are p, the roots of any scale multiple of f is still going to be p. Okay, so I'm saying a polynomial is irreducible if any attempt to factor it means you can only say it's this times a constant factor, right? Or that's to say I can't break it into two pieces where one of the pieces actually has degree less than the thing that I'm trying to factor. Something is always going to be equivalent to the degree of the original thing. Cool. Okay, but that's not the end of the story, right? Because depending where we're working, we're going to be able to reduce or not reduce. Okay, so consider this one, x to the fourth minus x to the power of 4 minus 4. This is going to have at least 3 different factorizations depending on what numbers we are allowed to use, right? So if I'm restricted to the integers, then x squared plus 2 and x squared minus 2 are irreducible. There is no polynomial with integer coefficients that divides x squared plus 2. Well, but if you let me use real numbers, or specifically, if you give me one extra number and that number is the square root of 2, or you're letting me work over I think some of you are taking Galois theory, the extension field of z extended by root 2, then this actually factors further, right? This thing here is actually encoding the plus minus roots of square minus 2. So you get an extra factor. Now this is the thing that's irreducible. Why couldn't I factor this in R? Yeah, I need a complex number for this, right? Okay, so what happens if I use the complex numbers? Okay, then everything factors into a product of linear factors. This is called the splitting of f, and this is why fields like C are called splitting fields, right? Because any polynomial with integer coefficients is going to be factorable into linear factors over C. Okay, so just be mindful of this, that like the term irreducibility has context. We're differently irreducible in different number systems. Okay, so we're going to focus on the Z number system and then the ZP number system. That's the only two we have to worry about. One of them is a ring, the other one is a field. Okay, so irreducibility means you can't break your polynomial into other polynomials in the current coefficient system that you're working in. Okay, so that's cool. So the object is going to be to take f then and to decompose it into irreducible polynomials, right? The same way that we take 12 and we can factor that into 2 squared times 3. We're going to want to take a polynomial and factor that into f naught squared times f1, where both f naught and f1 are irreducible in the ring. Make sense? The other thing that we have to realize is, so if we're factoring 12, and you said, okay, and you sent me off to do that factorization. You said, Paul, what was that factorization? I said, oh shit, it's 2 times 3, but I lost all of the degrees. Sorry about that. How furious would you be with me for that? Not very furious, right? Like getting 2 and 3, getting the prime factors was the hard part. Recovering their degrees would be simple. You just you just divide the 12 by 3 as many times as you can, 12 by 2 as many times as you can. Okay, so we're going to make some simplifications. One of them will be that if we solve the factoring problem to factor into irreducible components without any powers, that's fine, right? So the analogy here would be like, I tell you the prime factorization of 12 is 2 times 3. And you're satisfied with that because you can just do a little bit of extra work. Right? So we're going to solve sort of that lesser problem, even though in the code we do this recovery step by recovering those degrees. Okay, so history lesson. So back in the 1970s, when like computers started being sort of powerful enough to start being deployed on problems that humans couldn't yet do. We obviously tried to solve this factorization problem, and this is the first way that they developed in order to factor arbitrary univariate polynomials. So it relies on knowing how to factor integers. Okay, so I'll premise this. I know that factoring integers is an intractable problem. And in some sense, it's pointless to reduce a computational problem to that of an intractable problem. But it's better than not having any algorithm, period. Okay, so it's better to have a slow, bad algorithm than no algorithm at all. Because it's not necessarily the case that you're only going to try to factor things that correspond to unfactorable numbers or hard factorable numbers. So I'll show you how this works. It's kind of cute. So we want to factor 9x to the power of 4 minus 1. We want to separate that into irreducible polynomials in Zx. Something that's easy that a computer can do is evaluate a polynomial. Okay, so if I take 9x to the power of 4 minus 1 and I evaluate that at x equals 10, you get back the number 89,999. And if we presume that we can factor integers, then the factorization, then we know f of 10 is equal to 7 times 13 times 23 times 43. Okay, so that would have potentially come from 4 factors. So where did 7 come from? Well, that could have come from the factor x minus 3, because 10 minus 3 is 7. Same for 13. That could have come from x plus 3. 23 could have come from 2x plus 3. 43 could have come from 4x plus 3. Okay, so I say maybe the factorization of this is this, or like maybe one of these is a factor of this. So what I do is I do this evaluation, get this prime decomposition, say maybe this is it. And this gives us a reasonable guess at the factorization, or at least a reasonable guess at like one of the factors. Okay, so then you would take this and you take the GCD of that. You would get all of the common factors between this and that, remove them, and then you're left with a smaller factorization problem. So you just repeat all of this. Okay, as it happens, none of these divide this, right? So damn it, right? This is a Monte Carlo type of algorithm. You should expect that we're going to get unlucky sometimes, right? The casino house always wins, right? So in this case, house is 1. So, okay, let's just move on. Let's move on. Let's try a different evaluation point. Sorry, we're not going to try a different evaluation point. We're going to try different groupings, right? So if let's look at here, maybe this was 7 times 13. Maybe I shouldn't have maybe those two things came from the same factor. Okay, so 7 times 13 is 91. 91 is 100 minus 10 plus 1, which corresponds to x squared minus x plus 1. Maybe this is a factor of f. Nope. Damn it. Okay, let's try another grouping. Maybe 7 times 23 was actually the factor. That's 161. That corresponds to 200 minus 40 plus 1, which is 2x squared minus 4x plus 1. Damn it, does not divide f. Let's try 7 times 4d3. That's 301. That's 300 plus 1, which is 3x squared plus 1, which does divide f. So we have found a factor. We can then remove it using a division, right? Get the quotient, and then recurse, right? You just have a smaller factorization problem to solve. So that's one way that we could have done this. You can get luckier even by choosing different evaluation points, which have fewer prime factors. Because if you have fewer prime factors, the less likely you are to choose not enough of them to form the factor that you need. Okay, so if I evaluate this function at 12, you're going to get 186,623, which corresponds to the factorization 431 times 433. 431 could have come from 400 plus 30 plus 1, or I guess, how did they form this one? Anyway, it came from 3x squared minus 1, and 433 came from 3x squared plus 1. Oh, this is 12, not 10. Sorry about that. And in fact, that's just the factorization period. So we got super lucky this time, or we can get super unlucky, right? Where we generate something like this and there's many repeated smaller factors, right? So in any case, we don't do this. We can't factor integers, right? But this did work, and it is cute, right? So it worked well enough in the 70s. Okay, so that's not what we want to do. What I want to do is something else. Okay, so we're going to actually start now solving this problem properly. But in order to do so, I'm going to have to define a bunch of terminology because we need to clean the problem before solving it. right? I want to make some simplifications to it that ultimately don't matter, but are going to help us. Okay. So first, notice that I don't care about scalar factors on my polynomial, right? If a has a root, k times a has exactly that root. Multiplying a by a non-zero k cannot introduce more roots, right? So scaling a polynomial, it leaves its roots invariant. So, okay, I don't care about scaling factors. So therefore, the first thing I want to do is look at my polynomial and ask if someone's multiplied it by a scaling factor. Were you sneaky? Did you multiply this f by 3 before giving it to me? I want that 3 out. Okay, so if you take the GCD of all of the coefficients, you get something called the content. Right? So if you take f and you multiply by 3, that at least is going to have, like, 3 will divide the GCD of all of its coefficients, because 3 has multiplied every single term. Okay, so if I get the GCD of all of the coefficients, that's called the content, and I divide that out by the polynomial out by that, it's now called primitive. So a primitive polynomial has not been scaled, right? If you take the GCD of its coefficients, it's 1. Okay, so first, remove any scaling factors. The next thing I want to do is make the polynomial monic. That is to say, I want to assume that the leading coefficient of my polynomial is 1. Why? If you factor a polynomial whose leading coefficient is 1, what are the leading coefficients of the factors of that polynomial? 1. Because we know predictably what the leading coefficient of a product is going to be. It's the product of the leading coefficients. Okay, so if I insist that we're factoring a polynomial with unit leading coefficient, then I know all of the irreducible factors I'm going to produce are also going to be monic, right? So this is just another simplification. So all that's required of us to make a polynomial monic is to divide through by its leading coefficient. And we just have to remember that, right? Because we'll just put it back once we're done factoring. Now, I saw some raised eyebrows about dividing, but remember, we're eventually going to be we're going to work mod p, right? So dividing, you can just think multiply by the inverse. Okay, so making a polynomial monic is easy. When the coefficients are taken from a field, then we're just multiplying by the inverse, and then we just remember it, and then factor, and then stick it back. And we'll just call that one of the factors. All right, so the content of the polynomial is the GCD of its coefficients. As I mentioned, there is a function in your Julia project that is doing it. The primitive part of A is its A with its content removed. There's a little bug regarding this because, so technically here you're dividing, but we're dividing in such a way that we don't actually need a field. Okay, so in the sum of the integers are divisible by one another, right? I can do 4 divided by 2. Some polynomials are divisible by one another. Like I can take x plus 1, x minus 1 and divide it out by x minus 1. To build a better system like this, what we were supposed to do is let polynomials exist in the largest ring possible until they encounter operations which force them down certain paths. Like it's okay to divide 2 polynomials together, provided that you never, like everything clean divides, right? So that's how Maple is set up. So here, prim part in your code actually requires you to give it a prime, which is a problem if the content is a multiple of that prime, because we don't actually need to do it over mod p. This is guaranteed to be a clean division because the coefficients will all have that multiple. So anyways, if you come across some weird bugs, that's one of the reasons. Now here's some examples. So the content of this is going to be 3, right? 3 divides every single one of its coefficients. And therefore, the primitive part of this polynomial is going to be this with 3 removed, right? So 2, 1, and 1. Second, given a polynomial to factor like this one, we're satisfied finding only the irreducible components without the degrees. Remember, I'm totally satisfied factoring 12 into 2 times 3. And in the same way, I'm saying, okay, we're actually going to factor by just finding the irreducible components, and then we'll just do trial division to recover the degrees. That's simple. Okay, so that's the more simplified problem that we're going to be working with. We're going to be factoring monic primitive polynomials into irreducible components that don't repeat, right? And then we'll recover the degrees back later. Okay. So we're going to be doing this factoring in multiple steps. And the steps are as such. We do a square free factorization, then we do a distinct degree factorization, then a distinct degree splitting, and then sort of we put that all back together. So this is step 1. Okay, so I'm saying I don't care if roots repeat. Right, so what does it mean for a root to repeat? That means it has to have some higher power. Like an x minus 1 times x plus 2 cubed, the x plus 2 is a repeated root that repeats 3 times. This is kind of confusing. So a square-free polynomial does not have any repeated roots. Okay, it's kind of weird. Okay, so I'm saying a square-free polynomial doesn't have squares in it, which means it also doesn't have cubes or fourths or fifths, right? Saying the polynomial lacks any squares is actually a statement saying that the only things that it has are ones. Does that make any? I know it's a confusing. Anyway, to be square free also means you have no repeated factors. So square free polynomials, as their name suggests, are polynomials with no repeated factors. A factor that repeats 3 times also repeats 2 times. So that's why we're saying square free, because it implies cube free and quartic free and so on and so forth. Here's a technical definition. So a and f of x is square free if a has no repeated factors. That is, there is no b such that the degree of b is greater than 0 and b squared divides a. You can't find a polynomial which you can square which divides the original thing. And then we define a square free factorization to be this. Right? So be careful. Here I am not presuming that these fi's are irreducible. We have no, that's basically factoring already. I'm saying, look, if you can give me your f so that like all of the roots that are not repeated are grouped together, and all the roots that are repeated twice are grouped together, and all the roots that are repeated 3 times are grouped together, then we call this a square free factorization. Right? So this f can have arbitrary degree, but the point is that it factors into irreducible components that aren't repeated, that are square free. Okay, so this is the objective. Here's the lemma. A and ZPX is square free if and only if the, oh, this is old. Oh no, there shouldn't be a P here. That's obviously wrong. So in ZX, right, A is square free in ZX if and only if its GCD of A and A prime is equal to 1. The reason I can't put that P in here is because if you have roots that are repeated P many times, when you take their derivative, that P is 0. So screwy things happen. And there's ways to correct for this, but I don't want to get too down into the weeds. It's hardly a problem. This is why we say things may break on small primes. Right? This is why 3 currently doesn't work, because it's very easy to generate a random polynomial with roots that repeat a factor of 3 many times. I can give you the code to correct this. There's like a cute... it turns out when this happens, we know explicitly what the square free form looks like. There's some like neat number theory that you can play with, taking things. When you take things to powers of p, mod p, there's like really predictable things happen in those types of settings. But it's not really that important for us because we're doing Chinese remaindering. Like if you pick a prime that's unlucky, you just choose the next one. Like we're not really trying to factor in a specific ZP. We would want to, like that should be part of the system, but the problem that we're solving doesn't actually require it, right? So you can it's a Monte Carlo algorithm. We're just going to consider P's that are degenerate, bad, unlucky, move to the next one. And if you pick P very big, it's extremely unlikely that this is going to divide the root of one of your polynomials. But anyways, that shouldn't be here. But I did... Oh, well, anyways, this is old. I did make some corrections that shouldn't be there. I added something that says be careful because this technically isn't always true. This will not be true in ZP. But in any case, so if A is in ZX, A is square free if and only if its GCD of A and A prime is 1. So this is great. We have like a really fast way of checking if a polynomial is square free, right? Because derivative is fast, GCDs are fast. Both of those 2 things should be fast. Huh? Derivative with respect to x. And that's truly easy, right? It's just a linear operation where you just pull the degree down and multiply. Because we imagine when we're doing this, we're just imagining everything has been expanded. Like that's what's being held by the system. We don't even really need product rule, or we just need the one rule saying how to take the derivative of a single term. And I believe that's what we did. Okay, here's something really remarkable though. Okay, so suppose we have a and zx, and we know a has this square free factorization. The GCD of a and a prime is this. Okay, so this is really important, right? So suppose I can write a like this. It's a product of irreducible polynomials that are repeated once, a product of irreducible polynomials that are repeated twice, a product of irreducible polynomials that are repeated 3 times. If you take the GCD of a and a prime, what you're going to produce is this product with all of these degrees decreased by 1. And then this f1 disappears. Why do I care about that? Well, what happens if you take this polynomial and you divide it out, you divide out by a by it? Well, this was a. This is GCD of a and a prime. And this is what we get left. So what is it in fact done? It's stripped the factoring problem of all of the degrees, which I said we can recover anyways. Okay, so this is going to be one of the steps of our factoring algorithm, is to take away those degrees without factoring anything, which is the remark. So I haven't factored anything. I've just done divisions and GCDs effectively. Right, so a division in a GCD allows me to take an arbitrary f and produce a square-free polynomial from it. Right, so now instead of factoring this, we're going to factor this, which will be easier. Right, and then we'll just do trial divisions in the end. Okay, so step 1 in our factoring algorithm is to do a square-free factorization, which is easy because the square-free factorization is given by a divided by GCD of a and a prime. Okay, except for this caveat where things can get a little bit screwy if one of those degrees is a multiple of p, where p is the thing that you're working on. But we'll just say, okay, next one. That's just bad. Although there is a way to fix this. Maybe I'll post it on EdStem, the correction, because it's remarkable. It's fairly remarkable. Okay, so oh no, here it is. Warning: lemma 2 holds only when a in ZP, provided a does not have factors fkk where p divides k. So you can have a repeated factor of degree k where p divides k, but it won't be a big deal. Okay, so here's an example. So when I write something like this, you have to imagine in your head, we don't actually have this. The computer is storing this, the product, expanded. It doesn't actually know the factors, but mathematically it's equivalent. Okay, so when you see something like this, you have just remember the computer is holding something of degree 4, 6. No. Okay, so to cube this, we get x squared, x squared, x squared. That's a 6. To square this, we get a 6 here. So it should be x to the power of 12. Okay, so the computer is holding a degree 12 polynomial expanded, but that doesn't prevent me from taking its taking its derivative, and it doesn't prevent me from taking GCDs. Okay, so if I take the GCD of f and f prime, we're going to get this. And I'm telling you, if we take f and you divide out by this g, and then you factor what remains, this is what you get. You get the original f with those degrees removed. Right, so this should just give us a little bit of confidence that things are sort of working. And let's see if this does it. I assume that works because this is oh yes, sorry, this is different. Yeah, so I'm just saying take this and cube it. What's its square free factorization? Well, just what's inside, x squared plus x plus 1. But I don't know why we're getting all of, oh yeah, because it's been multiplied by 35. Right, so I don't care about things being scaled. Let's just see if this will work mod 3. I don't think it will. Oh, I got lucky. Why did I get lucky? Okay, well, let's not look a gift horse in the mouth, but let's see it. Oh, because I fixed this. Yeah, in my code, it's fixed. In your code, it will be broken. Sorry about that. Yeah, sorry for making my software more fully featured when demonstrating to it. But I think this shouldn't work for you. But if all you have to do is replace the square free part, that's where the code currently doesn't work for small primes because we can't get the square free part of that polynomial, which is like the pre-screening process for factoring. So it wasn't that bad of a change. Now, if you want me to make everything work mod 2, yeah, that takes a lot of work. Right? Let's not talk about the prime number's weird brother, right? That is also somehow even. Okay, So we can get now you can take a polynomial, we can remove its content, we can make it monic, we can make it square free. So now we want to solve, how do we then factor that? That becomes the problem. Now we actually have to start doing true factoring. Okay, so first, the thing I want to set some parameters. P is a prime and it's an odd prime, so it can't be 2. Right? With a very special case for P equals 2. All right, so everything that you're choosing has to be P greater than 2, probably even P greater than 3. Okay, so we're going to let A be primitive. That is, it has unit content, square free. That means none of its factors are repeated, and it's also monic, which I don't think I mentioned. Right, so this is the objective of this section, to take A and to decompose it into a product of irreducible components. If P divides the leading coefficient of A, choose a different prime. Like, we're done. Like, this sort of is if your leading terms disappear, that's a problem. That is to say, your image mod a certain P doesn't leave roots invariant, right? Especially if you're removing the leading term, right? So don't choose a P which divides the leading coefficient of A. But why shouldn't this be why is this not a problem anyways? What's one of the screening steps? Yeah, make it monic, right? Like, make sure it has a unit leading coefficient, right? So nothing's going to divide 1 except 1, which isn't prime. So this doesn't really matter as soon as we like stick the monic requirement on. Okay, so here's an example: 9x4 to the power of 4 minus 1. We factored this a bunch of times, but let's just do this factorization like mod different places, right? To notice something that the number of roots can change depending like what field that we're factoring over, right? So for example, if we factor mod 5, we split A into 2 polynomials of degree 2. If we split mod 7, we split A into 1 degree monomial of degree 2 and 2 linear ones. And in those 2 cases, the product is 4. That's fine. If we do it mod 3, noticing that 3 divides 9 and that eliminates the leading coefficient, we just get A is equal to 2. And that's just like, that's not a factorization of A, not by a long shot. Okay, so just keep this in mind. But this is actually useful information. Why? I've been talking about irreducible polynomials. How do you know that a polynomial is irreducible? Can you test for that? Like, I give you a quadratic equation. I give you a parabola. And I say, can you factor this into linear factors, like over the integers? You'd probably, you'd look at its discriminant, right? You'd say, oh, as long as the discriminant is positive, then I can do this. Okay, so but that's using a closed form. You're cheating, right? How do I determine if like a polynomial of degree 7 is irreducible? What happens if there's we have characteristic 0? Like, what happens if we're going over the integers? So I give you a polynomial. It's over zx, right? Its roots can be any integer, right? So I agree that testing that would have been a good idea, except when do we stop? I don't know. Not over zx. So here's a way that you can do it. So if we denote by dp the set of possible degrees of factors of A inferred from doing a factorization over zp, then we can utilize that information to deduce if a polynomial over zx is irreducible or not, which is kind of cool. So for example, here's A. I'm saying, tell me if this is irreducible or not. I say, okay, I'm going to factor it mod 2, and I'm just going to factor into a linear term and a quartic. So its set of possible degrees is so the factorization is either going to be into linear and quartic or a degree 5. Right, so that's why I'm saying like what we can infer from doing the mod 2 factorization is that this original problem breaks up into 1 and 4 or just 5. What can I infer from doing it mod 3 that it breaks into a linear and a quartic? Is that again, it's either 1 and 4 or 5, right? The factors. Over A, this is a bad prime because mod 5, everything vanishes. A is not 0, so he's okay. Bad prime, just go on to the next one. I do it mod 7, and I get that this is the product of a quadratic and a cubic. So the possible degree sequence here is that, okay, so you factor into a 2 and a 3 or a 5. Okay, but this has to be true generically, right, for Zx. So really, Zx can only have a decomposition into the intersection of all of these degree factorizations. So what is the intersection of all these sets? 5. That means what? The only thing that we can factor this into is a polynomial of degree 5. It is degree 5. Well, then I guess it's irreducible, right? So there you go. There's it given an arbitrary polynomial over Zx and the ability to factor mod p, you can determine if that polynomial is irreducible or not. There's a test for that, which is pretty cool, right? Because you'd like to know if you're trying to factor something, if there's even a purpose to, it's nice to know if a problem is solvable before you solve it. Now, I regret saying that because all the mathematicians are like, see, you do like existence proofs. You do like knowing the thing exists when you're finding it. Okay, maybe sometimes. Okay, Cantor-Zassenhaus factorization. So we now have a polynomial. It's been cleaned in various ways, right? So it has a unit leading coefficient, no content, it's square free. And what we want to start doing is like factoring it properly. Okay, so like so the only thing that we know at this moment is it has no repeated roots. So like, what are some ideas? Like the tools that are disposal are effectively like arithmetic and the GCD operator. Now we're over ZP. So now we can start using my colleague's ideas over there and like really to start doing trial divisions of everything, right? So if I were to say, I'm going to give you a polynomial, how do you know if it has roots mod P? It's like, well, try them all, right? Does it zero out at 0 or 1 or 2 or 3 or 4? And if f of 4 is 0, then x minus 4 necessarily divides your polynomial, right? Okay, what happens if p is big? What happens if this evaluation is expensive? Is there faster ways that we can do it? Okay, yes, conceptually, instead of doing trial divisions, why don't I just make the product of all linear factors? That's this, right? X minus 1, x minus 0, x minus 1, all the way up to x minus p plus 1. That's the product of all linear factors. It's going to have degree p. I think so. P or p minus 1. Remember, all the arithmetic that I do in this class is within tolerance of plus minus 1, right? Because of the stupid 1 indexing. Okay. Do you agree that if I took the GCD of A and all of the linear factors, that what I would recover is a product of all of the linear factors? Okay. So then what do I do with those product of linear factors that I've pulled out? I need to further reduce it. Right, so again, remember, we have f, it's not factored. I've taken its GCD against all linear factors. And now what I'm holding is all of the linear factors of f, but they're multiplied together. How then do I decompose that? Okay, so what I'm going to do then is say, oh, well, take half of them, half of the linear factors, and then take the GCD of that new thing you're holding. And 3 things are going to happen. One of 3 things, exactly. The GCD of the new thing and half of the linear roots is just the new thing, right? So all of the roots that you found are currently within the half of the roots that you're taking the GCD against. That's one option. That's bad. The GCD can be 1. So none of the roots of A are in the half roots that you've chosen. Also bad. Third option, some of the roots of A are in half of the roots that you've chosen. So what you end up getting is a proper factor of A. Why is this important? Well, if I get a proper factor of A, I can divide it out. So this product of all the linear factors I have, now I have a break point in it. I can break that into 2 pieces. And those 2 pieces are smaller. Okay, do this again. Okay, until the thing that you're left with is a linear polynomial. Do you agree this is going to let me factor all of the, I'll get all of the linear components by doing this? Cool. Usually that requires more explanation. But like this begs the question, what? Like, how do I do this, right? Like, how do you just spin up the product of all linear factors? What other problems? Well, what about the nonlinear factors? What about quadratics and cubics and quartics? we can do the same thing. Like I can say, go ahead and take the product of all quadratics, but we do so much more clever than actually constructing this. And this is why this factoring algorithm is amazing, right? Because of some of these observations made. Because very special things happen when working in number fields of prime characteristic. This is why we love working in them. Okay, so keep this in your mind. This is the objective, okay? So I'm going to take a polynomial which has no repeated factors. I'm going to take the GCD of all the linear factors in it and get all of the linear factors out. And then to factor those product of linear factors, I'm going to repeat that sort of idea, but only take half of the linear factors. And if since this is kind of stochastic, since we're going to get either A1 or a proper factor of A, you may have to permute, right, these roots around. And I'm saying all of those things that I just described are going to be algebraic operations, right? Like we just have to multiply and divide by stuff to do this, right? But that's the general idea. If we could do that, we would be able to factor. Cool beans. Okay, so distinct degree factorization. So step one is to take the square-free polynomial and factor it so that all of the linear terms are grouped, all of the quadratic terms are grouped, all of the cubic terms are grouped, and so on and so forth. And we're going to accomplish this by doing GCDs. We're not factoring anything, we're just doing GCDs, which is a nice fast operation that only depends on remaindering, effectively, and remaindering and adding. So here's Fermat's little theorem. Oh, that's an L in between there. This isn't fits. This should be a script L. Do you know Fermat's little theorem? It's this. So if you have a prime that's not 2, so a non-even prime, and you choose A, right, between 0 and P, less than, strictly in, right, 1 to P minus 1, then it is the case that A to the power of P minus 1 is congruent to 1 mod P. This is effectively like the definition of characteristic in a ring, right? The number of times that you can add something to itself before you hit, I think in this case 1, but it may be 0. But this is true in every ring of prime characteristic, right? A to the power of P minus 1 is congruent to 1 mod P. This means that A to the power of P is congruent to A mod P. I just multiply both sides by A. Agree? This means that A to the power of P minus A is 0 mod P. Also agree? This is very important. Okay, so the Fermat's little theorem implies A to the power of P minus A is congruent to 0 mod P for any A. Okay, let's just check this. Here's 5. A is 5, P is 23. This should kick out 0. Okay. Okay, so we blew the trick here, but let's study it. Why isn't that 0? So this is important. This is where the interplay between computer science and math. This is the section of math I occupy, right? Because computers can't do things that mathematicians can do. So what happened here?
Feel like overflow because you have a fixed number of bits.
Yeah.
wrapped around.
15 to the power of 29 is big. So big, in fact, that it exceeds the 128-bit integer. Okay, so this actually isn't wrong. We've just done a mod 128-bit computation, which isn't the thing, but I want to be working in the integers. Okay, so if we like repeat this computation, but like explicitly say, look, use arbitrarily sized integers, then it works. Okay, so this is illustrative of something. We need this as a in computer algebra. I need integers to act like integers. I don't need integers to act like their mod P counterparts, like when I don't want them to be, right? So the Chinese remainder theorem is a cope, effectively, to not have to do this. Okay. The other thing is, so how can we fix this? Who's completed the project or gone all the way down?
That project be kind of like on each step, potentially of the multiplication, you can just keep modding just so you never like get to.
Yes, that's one of 2 optimizations that you can make. So consider taking 8 to the power of 17 cubed. Okay, if I were to put that into the system, it's going to say it'll print out 7, followed by 10,000 digits of numbers, followed by 8, mod 17, 9. Okay, so in order to conclude a 9, we needed to compute a number with 10,000 digits in it, knowing that the answer could never exceed 9. Okay, so the first idea here, and this is part of your project, you need to do, part of the factoring algorithm is to take something to a high power. So we need this optimization in order for the computer not to blow up like this. Okay, so the first optimization is don't let the product swell to something huge and reduce it after everything. Right? Do this reduction every single time. Do all of the operations mod 17. Right? So you don't do 8 times 8 to get 64 and then multiply that by 8. You do 8 times 8 to get 64 mod 17, right? Which is going to be something less than 17, which you then multiply by 8. So good on you. That's not the only one thing that we can do, though. What's something else that we can do? So even if we were to do your idea, how many multiplications does this require? 8 to the power of 17 cubed. This is like so many multiplications, too many multiplications. So instead of doing these 17 cubed many operations, we're going to do something called repeated squaring. This is a very common technique, sometimes called big step, little step. Because I don't want to multiply by 8. Right? What's better? You take the thing that you just computed and multiply it, square it. That's still one multiplication, but you're going much faster. So if you took 8 and squared it, that's 8 squared. If you squared it again, that's 8 to the power of 4. Squared again, that's 8 to the power of 8. Right? So one person could have done 8 multiplications to do that. We did 3. And this is just going to get much more severe as we keep squaring. Okay, so we want to do that here. Okay, we don't want to sort of do all of the products. I want to square as much as I can and then multiply those squares together. So if you look at something like, suppose I want w to the power of 103, you just look at the binary representation of 103, right? Because it's giving you powers of 2. So 103 is 64 plus 32 plus 4 plus 2 plus 1. Right? So instead of doing w to the 103, I can do w to the power of 64 times w to the power of 32 times w to the power of 4 times w1, right? And I can do this for any integer that has a binary representation. That is to say, all of them, okay? So if we can do this, then it just remains to figure out how we actually get 1 squared 4 32. Well, this, right? Take w, square it again, square it again, square it again, square it again. So to get w to the power of 64, that took 1, 2, 3, 4, 5, 6 multiplications. Okay, and then you do, so you need 6 multiplications to get this, 7, 8, 9, 10 to do w to the 103, not 103. Okay, and you believe me, it's going to be a lot more significant in this situation. Okay, so that's the other thing that you have to do in your project. It's not overly hard, but it is super important, right? Because like this seems really innocent, right? That you just want to do some arithmetic. It's like, well, it's going to be expensive and wrong. Like it's like the worst of both worlds. Okay, so if you take one thing from these lectures, this repeated squaring or this big step, little step is really useful often for getting well, when you have to do something repeated multiplication. So there is pseudocode in here for you to do it. So you don't actually have to like figure out how to make it an algorithm. I've done it. You just have to understand enough of this method to understand this, and then enough of Julia to be able to make that translation. Right? So if you have problems, just talk with me and Yanni. But just, this is effectively the Julia code, right? Just a minor pivot. Any questions about that? Because that is explicitly part of your project. Yeah, it is cool. It is cool. Okay, going back. Where were we? Here. Okay, so we have this Fermat's little theorem, because I'm going to be taking things to powers. Now we don't care how big those powers are. Here's a corollary. Okay, so remember, it is the case mod p that a to the p minus a is congruent to 0 mod p, right? Remember this thing here, important. I'm going to spin up a polynomial. f of x. F of x is going to be x to the power of p minus x. This means that if I evaluate this at any element from ZP, what am I going to get? It's a to the p minus a mod p. It's going to be what? 0. 0 every time. Okay, so if f is 0 at every element in ZP, what is it? It's the product of all linear factors. Isn't it? Isn't that the thing that we need to take GCDs of against f to get all of the linear factors? Did we need to do any multiplications to get this? No, because that's it. It's x to the p minus x is that polynomial of all linear this statement. I wish I could circle stuff, but this is super important right there. X to the p minus x mod p is the product of all linear factors mod p. Cool. I know how we can use this, okay? So we just need to take f, which has been sanitized a bit, take its GCD against x to the p minus x, and what that's going to give back to us is the product of all linear factors of the thing that we're trying to factor. Now, they're not going to be factored for us. We're holding something, maybe like a quintic or something like that, but I'm assured that the thing I'm holding is going to factor into 5 linear factors. Cool? Okay, so what do we do for the rest of them? This is even more cool. Okay, I can't really explain to you why. Well, I can. It would just I can't explain to you why in the next 10 minutes. But x to the power of p to the power of k minus x is the product of all monic irreducible polynomials in ZP of degree d that divides k. Okay, so that is to say, x to the power of p minus x is the product of all irreducible linear polynomials. X to the p squared minus x is the product of all quadratics. But some of the quadratics are reducible. Okay, so take the thing that we just computed and remove them. Okay, so what's left now is going to be the product of all irreducible quadratics. Okay, go to the cubed. Okay, so this is going to contain all irreducible cubic factors. Okay, well, let's just remove all of the, well, cubics sometimes factor into linears and quadratics. Okay, remove those. We've already calculated them. So what's left is the product of all irreducible cubics. That is to say, if we continue doing this procedure, GK is going to be the product of all irreducible factors of a degree K. So now it should be clear that given our sanitized input polynomial f, that I can separate it into the product of linear factors, a product of quadratic factors, a product of cubics, quartics, synctic, and so forth. This procedure is called the distinct degree factorization. I've taken the input polynomial and I have factored it into factors that are distinct in their degree, if that makes any sense. Even though the group that holds all the linear factors may be like a quintic or something like that. Like more stuff has to happen. Okay, so here's some pseudocode for doing it if you wanted to do this in Python or something like that. Here's the Julia code for doing it. You can just sort of look at the pseudocode and see how it ports over to the Julia code. We can see that it sort of is working. Okay, so here's my input polynomial, 7x to the 5 plus 9x4 plus 11x squared plus 9x plus 1. Look how beautiful that printed, by the way. So nice, that Unicode. And I'm saying, okay, the product of all linear factors is 16x plus 9. That is to say, that is the only linear factor of the system. And I'm saying the product of the quadratics is x to the power of 10x to the 4th plus 13x cubed plus 15x squared plus 5x plus 2. So clearly this is encoding 2 of the quadratic factors. We just have to sort of then take this and split them. All right, so remember, square-free factorization was that very simple thing of just dividing out by the GCD of a and a prime. That leaves us with no repeated roots. The second thing we did was isolate those things into the groupings of linears and quadratics and cubics and so forth. The last thing that we have to do then is take those groupings and separate them. Right? So take the product of all linear factors and separate them into a list of linear factors. Take the product of all quadratics and separate it into a list of quadratics. And this is called distinct degree splitting. Now, how did I say that we were going to do this? The initial idea was to say, oh, take half of the roots, and then we'll try a GCD and hopefully we get lucky. Okay, well, I don't want to take half the roots. I don't want to have to generate that. I want to do something clever. Like I want to know exactly what half the roots look like. Well, we do know what half the roots look like because thankfully, differences of squares are super easy to factor. Remember, x squared minus 1 is x plus 1, x minus 1. Okay, but if p is greater than 2, then I can factor out an x here. And you get x, which is that's the 0 root if there is one. X to the power of p minus 1 minus 1. What is this? Remember, p is not 2. Therefore, p minus 1 is even. The p minus 1 is definitely even. So it's a difference of squares. Which difference of squares? That difference of squares. Right? Half of p minus 1 and plus 1 and minus 1. Agree? Right, but I said this is equal to that product. Didn't I? This is supposed to be equal to the product of all linear factors. But the product of all linear factors is equal to this? Oh, then this is equal to half the product of all the linear factors. Is it not? So I don't need to find the product of all half the linear factors. It's just that. I don't have to actually form it. I just know what the form is a priori. Okay. So then again, I now have my product of linear terms that I'm trying to split. I give it to the GCD algorithm with this, and I hope to get lucky. I hope to not generate the unit or G. I hope to generate a proper divisor. If I don't get lucky, then you try it against this, right? You say, okay, I'm not going to do x to the p minus 1 over 2. I'm going to do x plus alpha to the p minus 1 over 2 minus 1. And the only effect this has is randomly permuting the roots, which is exactly what we wanted to do, right? So to pick a different random selection of roots, yeah, just do this linear shift. It's quite easy actually, which is amazing because we're just like materializing all of these special products that we need, which just happen to be predictable polynomials, which is awesome. And that's only the case because we're working in a field of prime characteristic. Okay, so similarly, we can play the same trick for the quadratics and the cubics and the quartics and quintics and so forth. Here it is explicitly, right? As long as p to the power of k is, well, this is going to be a product of odds, right? So subtracting 1 from it is going to make it even. So this is going to be a product of half the monic polynomials of degree k. Okay, here's a theorem. Suppose I take like an arbitrary element, a polynomial from ZP, and I'm saying it's the product of monic polynomials of degree k. Right, so I have gk. It's an arbitrary product of monic polynomials of degree k. The question becomes, if I were to take the GCD of that against sort of half of the roots of degree k, what is the likelihood that I'm going to get lucky? Because if that value was small, then this algorithm could be not useful. It turns out the probability is 1/2 minus 1/2, not 1 over 2p squared. A little bit less than half. And like way a little bit less than a half if you choose p big, which there's no reason not to, because we don't need to do anything over a specific p. We just need enough p's in order to exceed some type of bound. This is a problem if you really want to factor mod 3. If you want to know to tell math to let me do a computer algebra course, which I'd love to do. But it's about 4/9, right? The odds of getting lucky when doing this distinct degree factorization, which is to say, you're basically assured. Do it enough times, you're going to get lucky. 4/9 is basically a half, right? So on average, 2 and a bit. You're going to have to choose 2 and a bit primes. I also wrote a book on stochastic processes. If you want to buy that, I'll probably see a nickel. Oh yeah, which is like 10 cents. Don't write a book. It's the best way to make not a lot of money really slowly. Okay, so here's your algorithm for doing this distinct degree factorization. It just sort of puts into steps what I've been talking about. This is how it's been implemented in Julia. And then you can see that it works. Okay, so I don't actually remember what the problem was. Let's see here. Ah, I see. Okay, so no, I don't know what that did. Okay, anyway, there may be a little bug in here, but this is what it's supposed to. What is DD split saying it's doing? Yeah, I'll take a look at that when we go back. So anyways, the how much do I have left? Yeah, just 1 minute. We'll go over this in more detail when we return tomorrow. But this is just sort of like bringing it all together. Like you give me an arbitrary f over the integers, and we're going to clean it, like find the primitive part, make it monic, do the square root factorization, do the distinct degree factorization, do the distinct degree splitting, and then like reform it in the end. Right. So this factoring algorithm is just walking through the components of the larger factoring algorithm that we talked about. Okay. So go home, mull this over a bit. Like I did glaze over some of the details. So maybe tomorrow we can like go back into some of those details. But what would be best is if you studied this a bit and came confused and asked for some clarity on these things that are confused. So that'll be the plan for tomorrow. I'll rewatch these lectures. I'll isolate the things that I explained poorly and explain them again. And then I'll ask you guys what you want me to explain. And then any time left, I'll just help you on your projects if that's okay. Cool beans. You can ignore this. This is for years ago when we asked them to change the representation underlying representation of polynomials to sparse. But if you're interested, this is how you would do it. If anything, feel grateful that we're not asking you to do this in addition to all the other things that we've been asking you to do. Okay, go home. I hope you found that interesting. This algorithm actually is an amazing algorithm. The amount of things that just sort of like happen that are like miracles of number theory that just are great. It was cool. So see you guys tomorrow. Bye, chat. Yep, see you guys later. Thank you. I love when people are interested in the things that I'm saying. Chat, you around? I hope that was okay, technically speaking. Any signs of life? Log in and leave. Okay, I'm gonna shut it down. See you later. See you later, gentlemen.